Welcome. The title of today's lesson is Law of Cosines. And so we'll just continue our discussion of non-right triangle trigonometry. Take a look at a couple other definitive situations. We have now 3 scenarios that we've been looking at this point, really primarily using just law of sines. So ASA, and then AAS, and then SSA, that ambiguous case. And so what we're going to now do is navigate through a couple other situations where law of sines doesn't quite work out initially, so we need a little help basically. And so law of cosines will do that. All right, so there's a little investigation here. Just want to show you where it comes from, and then we'll go ahead and do just a couple examples here today. So I've got an oblique triangle on your paper there, and it says draw a height from angle C to side C and label it Y. So if you would, with me on this, just nice dotted line coming on down there. You can label it really anything. It looks like I asked you to label that Y. So if you can go ahead and do that on your paper, that would be great. And then let's see, it says number 2, label the length from angle A. So from here to the bottom of the height, we're going to label that X. So that would be from here to here is going to be X. Remember, the whole side is C, but from here to here we're going to call that X for the time being. And not to overplay this too much initially, but you don't have to do this piece, but I hope everyone sees that when I drew that height in, I have created a couple right triangles here, so we'll utilize a little right triangle trig to kind of help us out. Okay, so everyone, number 3 on your paper. Let's see if we can fill this in and start making some connections. Number 3, it says, write an equation for X in terms of angle A and side B. All right, so we're going to relate now X, A, and B together in this first right triangle. So everyone, focus on angle A for just a second if you would, and I'm hoping that you would see that basically the X value would be the adjacent side, and the B value from here to here would be the hypotenuse. So in reference to angle A, it looks like it's adjacent and hypotenuse. So on your paper, just over to the side here initially, let's go ahead and write the cosine of angle A, so that's adjacent over hypotenuse, and that's X over B. And it does say write an equation for X, so I'm hoping everyone's cool with the fact that I'm going to bring this B on up, and I get X equals, and this is what I'm going to write in here, if you could do the same. So B times the cosine of angle A. Okay, good. One piece taken care of. Now everyone, if you would, let's go ahead and still deal with angle A. It says write an equation for Y in terms of angle A and side B. So here's angle A, everybody. I want to talk about Y and side B. Still the same right triangle, everyone. Hope you all see that. And so let's go ahead and get these 2 pieces. It looks like in reference to angle A, opposite side and hypotenuse. And so I'm hoping you see this piece right here, everyone. It would be the sine ratio of our angle A. Just good right triangle trigonometry, of course. Is equal to the opposite side over the hypotenuse. And we did want it in terms of Y, so everybody, of course, take that B and let's bring it up to the other side there. And I'm hoping you see now that Y is equal to B times the sine of angle A. Now, I would have to go to my other screen. I'm going to try to hold off on that for just a second and kind of just read the next piece. It says, I believe, number 5 should say something like, write an equation for the other right triangle using the Pythagorean Theorem. Okay, so before I go ahead to my next screen, let's focus on this piece right here. This other right triangle, I put a little number 2 in there so you could see it. And I'm going to do a little Pythagorean theorem. This squared plus this squared equals that squared. Now these 2 kind of speak for themselves. The only dilemma is I don't really have a label on this one, guys. So what do you think? What is it from here to here? And rather than introducing an entirely different variable, I'm hoping everybody sees that C is all the way across, X is from here to here, so this should be C minus X. And now, everybody, do I have a nice little Pythagorean theorem with this, this, and this? Okay, I believe I do. So now I will go to my next screen, and it says exactly what I read there. And so I have basically this. That a squared, that's the hypotenuse, is equal to that first leg squared and the second leg squared. Everyone okay with that? So a little Pythagorean theorem with that second right triangle. This squared is equal to this squared plus this squared. Okay. Now, I only want to really deal with the sides and angles in my oblique triangle. And so I introduced the x and y here, and I think that's going to have to go here momentarily. So it says, substitute your expressions from steps 3 and 4 into the equations for x and y. So very simply what I mean by that is, I don't want x anymore, everyone. And I don't want y. I want all a's, b's, and c's, because that's what's in the original triangle. And so here's what it should look like. I get c minus, now remember I asked you to solve for x, and this is what x is, b cosine of a, good, and then a squared. And then instead of y, everybody, it should be b sine of a. Okay, so all I'm doing is just good math, guys, substituting one in for the other. And now, as you can see, it's all in terms of a's and b's and c's. It does say, as you're going to see momentarily here, and this is going to get a little hairy. I don't mind doing the work up here to kind of show you what's going to happen. We're going to expand this on out. And so this side is what it is, guys. It's a squared. In fact, that's going to be part of our law of cosines coming up momentarily. If I asked you to FOIL this, and you don't have to, it's all right. I don't mind doing the work here, but you should be able to at least see that my answer will make good sense. If I asked you to FOIL this times itself, you end up getting c squared, c times c. You would do outside and inside, which would give you this. You'd get two of these, 2bc cosine a's. And then you would, this times itself would give you b squared cosine squared of a. So that's just foiling this piece out right here. Now, guys, this happens to be a good little exponential property for us. If I asked you to remove the parentheses on this, you would take b squared and sine of a squared, and you would get this, b squared sine squared of a. Wonderful. Okay. Well, guys, I'm going to clean it up just a little bit. I'm looking at the back end there, and I'm curious if you see something. I kind of wrote a few things down on the paper, but it says, use algebra and a fundamental identity to simplify to some degree our equation. So everyone, this is what we're going to put in, and then we'll go ahead and write our law of cosines, but you can at least start to see where it is. So here's what I have, everyone. First and foremost, c squared. Everybody, that doesn't change. Now here's what I'm going to do. It's the back end I'm interested in. Does everyone see this? And does everyone see that these two terms actually have a b squared in it? Well, I'm going to treat that as a factor momentarily. I'm just going to factor that out. And when I do, I end up getting cosine squared plus sine squared. And it kind of gives it away on the paper. I used a little algebra right there, factoring specifically. And everybody, does the light go on when you see something like this? What is cosine squared plus sine squared? And cosine squared plus sine squared really is just 1. So you end up getting b squared times just 1. And this can essentially go away. When that goes away, you basically have your law of cosines right here. Okay, good. Some difficult math in there, but that is at least a way to see it in action, and so this is what it'll be. There are 3 scenarios just based on how you label the triangle, but they are all essentially the same. So I did it from the perspective of A. So now, as you can see, you get a b squared and a c squared. Everyone see that from just above? And then minus the 2bc, and there's your cosine, hence the law of cosines, cosine A. And again, it's just the lettering, that's all. So it's the exact same thing. So something like this, and then 2ac. Notice this angle is always opposite what's on the other side of the equation. So little b on this side, big B on this side. And then same thing here, everybody. You'd get a squared and b squared. Take away the 2ab, and it would be cosine of c. And we'll see this. We'll play it all out in just a few minutes. But that would be the law of cosines in a nutshell. Obviously, guys, you can see it's a little more complicated than the law of sines. So, just in terms of strategy, everybody, when we're working with the non-right triangle trig, if we can use law of sines, that's probably what we want to do. But if we can't, then we're going to have to rely on this one. A little more complicated, but we'll find a way through it. By the way, it just says what happens when the angle is 90 degrees. So look at the top variation if you don't mind. What happens if angle A is 90 degrees? And as you can see, if I have 90 degrees here, cosine of 90 degrees, everybody, is 0, right? And so if this is 0 right here, is everyone cool with the fact that this just all goes away? Because 0 times anything is just 0, and look what you end up getting. This would be the hypotenuse, by the way, and you would end up getting just the Pythagorean theorem. So it's kind of cool. The Pythagorean theorem is really just a natural progression of the law of cosines if that angle is 90 degrees. Wonderful. All righty, everyone. Let's go for it. So 2 more situations that we're going to see today. What's called SAS and an SSS. Now, they're definitive in nature, meaning if I have this piece right here, in example 1, if I have side, angle, side, there is only one way to construct the triangle from here. There's only one answer for little a, there's only one answer for little b, and there's only one answer for c. So we're going to have to solve it. Now we're going to have to be a little careful with this piece. It is a little more complicated, and we do have to kind of follow step by step here. All right. Well, again, when I see a non-right triangle, I always look to do law of sines because, quite frankly, it's easier. And I'm always looking for that constant ratio. Remember that? The side across from the angle. Unfortunately, with the information that's given in this problem, I don't have that. I have a constant but a variable. Constant but a variable. Constant but a variable. So no law of sines, unfortunately. So now I have to rest on the law of cosines. So law of cosines to find the third side. So everyone throw that into the mix if you would, please. And let's do exactly that. The good news is, if I'm trying to find little a, which is exactly what I need, then this is what goes on the side by itself, because the angle across from it is the correspondence. So what I mean by that, everyone, is it's a squared, and now it's perfectly set up for this. 8 squared, 7 squared, minus, though, 2 times 8 times 7 times the cosine of the angle across from little a, which is 64 degrees. Okay, now it looks pretty heavy, but the good news is the variable is all by itself already, except for the squared, of course, and all of the right-hand side is numerical. So all I have to do is grab the calculator and just let it ride. I'm going to do exactly that with you just to make sure. Even though I have this on my paper, I'm going to go ahead and bring my calculator up, and let's do it once together. So here's what I'm thinking. 8 squared. Add the 7 squared. But now I have to take away the 2 times the 8 times the 7 times the cosine of our angle, which is 64 degrees. And I'm going to hit enter, and I get that piece right there, about 63.9 and change. So the left-hand side is this, and the right-hand side is about 63.90. Now that's not too bad. One of the only mistakes I've really seen students make with this situation is forgetting just that we're solving for a, not a squared, so just make sure you square root. So of course, everyone, square root that if you would. And when you square root this piece, we're really close to 64, so which means square root there, very close to 8, and I get about 7.99. And so that is step 1. Okay, good. So law of cosines because I could not do law of sines. And that's great. Good thing was here, all this was numerical, and I let the calculator do the work. Just make sure you undo the square at the end. All right, now do you see it? Here it is, everybody. Now that I have this side, do I have one across from the other so I can start thinking about law of sines? Yeah. And so here we go. I would say it's law of sines. Now here's where we're going to have to be careful. Because if you really look at this in detail, I'm in a precarious spot here. If you see, everybody, I have a little SSA situation going on with the remaining piece. I have two angles to get. And unfortunately, with my two sides, really I know it's three sides, but no matter how we formulate it when we do law of sines, I'm going to have to do something that's going to be SSA in nature. And if it is, then I have to start doing all that interpreting from yesterday. And I don't want to do that. So there's a way around it. So guys, as a matter of fact, I would put a little asterisk next to this one. I did it on my paper as well. So what we're going to do is use the law of sines to find, and here's the key, the smaller angle. And here's what I'll write in. Because remember, guys, if we're in law of sines, when we do an inverse sine, it can only give us acute. Everyone okay with that? Inverse sine can only give us acute. And so if I have two angles left, if one of them happens to be obtuse, I don't know which one it is, but if one of them happens to be obtuse, the calculator won't be able to give it to us, and we wouldn't know. But if I find the smaller angle, obviously, guys, the smaller angle has to be acute. There can't be two obtuse angles in the triangle. So what we want to do is use law of sines to find the smaller angle. Inverse sine only gives the acute angle. So you can see, guys, this is going to be a little more complicated than the first day dealing with law of sines. Okay, so we have to decide, of course, here, because I want to do law of sines. And by the way, I'm just looking at this, and I know for a fact that's how we're going to start it. I want to use law of sines. It is easier. There's no question about it. But I do have to be careful here. And so I have two angles to choose from, either angle C or angle B. Now, I don't know that either one of these would be obtuse necessarily, but I don't want to risk it. So let's find the smaller one, because I know the smaller one will be acute, and an inverse sine will give it to us. So guys, which is the smaller? Angle C or angle B? Well, it has to be angle B, because angle B is across from the smaller side. 7 is smaller than 8, so angle B is smaller than angle C. So angle B is where we're going on this. So I have 7 over the sine of angle B. And we've been in this spot before, but now we are confident that angle B is acute. Absolutely, because I'm dealing with the smaller of the two angles. And so when we go ahead and do this, I'm going to go ahead and bring my calculator up. I have it, but I'm going to bring my calculator up and do it. You guys do it as well. So I have 7 sine 64, and then divide by 7.99. Okay, and that would be my sine ratio for angle B. And sorry for being redundant, there are two angles that have that sine ratio, an acute in quadrant 1 and an obtuse in quadrant 2. But now we know it has to be the quadrant 1 angle. So I do an inverse sine on that answer. Let's go back there for a sec. There we go. And I've got it. So angle B is definitively 51.9, I'm just going to go ahead and round right there, degrees. Outstanding. So this is 51.9 degrees. Excellent. 5 parts down, 1 to take care of everybody. Angle C is it. And so how about this? Just find the third angle. And as we all know, this should be relatively simple for us. Has to add to 180. And so I'll go ahead and put this piece right here. Based on what I have, 180 minus, what did we say, 64 plus the 51.9. Okay, and so this is angle C when all said and done. Let me just make sure I have everything correct up here for you. And I have about 64.1 degrees. So that is SAS. As you can see, a little different. And as I said, we're in a bit of a precarious situation. After getting that first side using the law of cosines, which was great, awesome. We got the 7.99, but then we have to be careful. If we're going to use law of sines, we have to understand its limitations. And with law of sines, you want to go with the smaller one. Okay? Let's go get 2, and then we'll wrap it up on 3. So a lot of this is can you draw and can you label things. So let's see if we can do this together. A vertical 20-foot telephone pole on a 15-degree slope is braced by 2 cables extending from the top of the pole to points on the ground 30 feet up and 30 feet down the slope. Find the length of each piece of cable. Alrighty. Well, guys, let's draw ourselves a nice slope here. I'm going to try to come on this side a little bit. So I see a 15-degree slope, something like that. And it wouldn't be a bad idea for you to pause the video for a moment and see if you can draw it out. You know, some of these word problems will have a drawing with them, some will not. You know, and a lot of good math goes into the interpretation piece. Can you read the problem and draw it out and then label appropriately and find a strategy to solve? So anyway, I'll go through the motions here. Pause at any time, of course, if you'd like. So a vertical 20-foot telephone pole, so something like that. There's your 20 feet right there. Is braced by 2 cables extending from the top of the pole to points 30 feet up and 30 feet down. Something like that. That's what I'm reading here. 30 feet up, 30 feet down the slope. Okay. And we're trying to find the length of each piece of cable, so we're going to find that, and we'll find that. Just a couple variables on that piece. Okay. Well, I do have 2 triangles here. That's the good news. So I have a side and a side right there in that one, and a side and a side right here in that one. I am missing some info, though, and so we're going to have to fill this in. Alrighty. Well, let's see if we remember our geometry, everybody, and see if we can work this out. I think that 15-degree slope has to come into play somewhere, and we have to relate it to these triangles. I don't know if it would be helpful, and I would do this very light on yours. I have somewhat of a limitation on mine, but I'm going to sort of draw in the horizontal right in there, just like that, maybe helping us out a little bit. Okay, now I guess I would ask you, based on that piece right there, and this 15 degrees, could you tell me the angle from here to here? Could you tell me this inside angle? What would be the rotation from here to here? And maybe using that same idea, could you find that? I don't know which one would be easier for you. Well, the way I'm reading this, everybody, is just through a little geometry. There's 15 degrees going up. This also, right in here, guys, has to be 15 degrees. So sorry, that's really difficult for me to write that in. But I see that as 15. From here to here, just what's called alternate interior, which means now I have a perfectly vertical coming in perpendicular to this horizontal right there. So that's 90 degrees. And so I have 90 degrees from here to here and another 15 from the slope. Well, guys, I'm seeing that as 90 plus 15, which would be 105. So take a look at my diagram, see if that works for you. But essentially, I'm seeing this angle as 105, and then this angle, which would have to be supplementary, and by the way, we could still use that 15-degree slope. Notice, perpendicular right here to here. Now just taking away this part, 90 minus 15 gives you 75. And now, guys, of course, it's just SAS. Side, angle, side. Side, angle, side. How about this? Make a deal. I'll do one. You do the other. We'll write both answers. So I'll do the smaller one. And this is a perfect situation if I want this right here. If I want that, this is across from this. One variable, one angle. So it's law of cosines with the x being on that side by itself. And guys, it's SAS, so it's 30 squared. It's 20 squared minus 2, 30, 20 cosine of the angle. Plays out beautifully. I actually have this on my calculator. On my paper already. I've already done the calculation. I end up getting just that whole right-hand side there as 989, give or take, somewhere in there, and which would mean about 31 and change. Excellent. Now, if you kind of look at the diagram here, not that I draw well by any means, but just sort of the nature of this is 30 up and this is 30 down. It's going to hit the uphill part of this quicker than it would the downhill part of this. So I'm seeing this one certainly is going to be a greater length than 31.46, and I'm hoping you would agree with that. And as it turns out, the larger the angle, yeah, certainly that's going to be the case. Alrighty, well, if you don't mind, you guys do this one. Pause it, please, if you would. Give me a little SAS and find y. Obviously, very, very similar, of course. Okay, well, I end up getting a y value here when I did this one. I get it as about 40.13 feet. So just check yours, and if there are any issues with your calculation, don't hesitate to ask. All right, nice one. Good little review just on SAS from example 1. To me, I think probably the diagram was 75% of the battle there, especially these two pieces, coming up with those two angles. Alrighty, last one, guys. And here we go. And so it is the fifth, and by the way, the last scenario that we'll be looking at here. And so it's side, side, side. And as a matter of fact, for a non-right triangle, if you know the three sides, there is only one definitive way to construct the triangle. And so what would be the angle measurements that would correspond to those three sides? Well, guys, that's exactly what we're going to have to figure out here. So if you remember in example 1, I had you put a little asterisk next to the second part because that was the one that was a little sketchy. And here, guys, this is the one I'm going to have you put a little asterisk by, the number 1. This is where it gets a little sketchy. So, first order of business. There is no law of sines to be had here. I do not have angle and side across from one another, unfortunately. I don't have it. So law of sines is out of the question. Law of cosines does work, and that's exactly what we're going to do, but we have to be careful and we have to be strategic about this. Now, I had said way back when you do an inverse sine, the unfortunate thing about inverse sine is it can't give you the obtuse angle. It can only give you acute. Absolutely the case. But let's see if you remember your stuff here. What happens when we're dealing with inverse cosine? Do you remember the interval for inverse cosine? I'm just going to write it up here. When we did inverses way back when, what we found is it's not negative 90 to 90, but it's 0 to pi, or 0 to 180 degrees. So everybody, as a result, if I do an inverse cosine and the angle is acute, it'll give it to us because this is in our interval. An acute angle is in our interval. But here's the great thing about it. If I have a negative ratio, basically that's what it's going to turn out to be, if I have an obtuse angle, an inverse cosine will give it to me because it ranges from 0 to 180 degrees. So here's the idea. If we have the choice to go with any one of these three angles here, we're going to find the largest first. So if you would, on your paper, just to get this moving, law of cosines to find the largest angle. And the reason is, of course, inverse cosine will give either one. It'll give us acute or obtuse. And so we might as well go ahead and utilize it just in case there's an obtuse angle in there. If we have to use law of cosines, we might as well go ahead and try to find the largest one just in case. So that's the key. Because otherwise, if we found, say, this one here, obviously, guys, this is a small one right here. If we found this one first using law of cosines, we would then be in SSA land. And if we were in SSA land, I would have to use law of sines, and then I wouldn't know if this angle is acute or obtuse by solving it. But with law of cosines, I take the thinking out, the interpreting out. I just know that this is the largest angle right here, obviously across from the largest side, 12 the largest side, so this angle is the largest angle. I don't know if it's acute or obtuse. Again, you can go by my drawing maybe and figure it out, but mathematically I wouldn't know using law of sines. But using law of cosines, it'll tell me. So, long story short, angle B, guys. Let's go find it. So here's what I have. If it's angle B, then we want to go ahead and use that side across. So we're going to be a little careful on this calculation. It is the 12 that stays on the side by itself using law of cosines because I'm trying to solve for angle B. And so everyone, it's 12 squared equals 5 squared and 8 squared minus 2, 5, 8, and the cosine of our angle. It is either acute or obtuse. When I undo this cosine at the very end of the game here, I should be able to give it to us. Now just be a little careful on this. I square things. I get everything taken care of first. So I'm going to go ahead and do this one step at a time, careful of shortcutting, because these numbers are attached to the cosine of B. So 2 times 5 times 8 is really minus 80 cosine of B. So just be careful here, everyone. Order of operations, you cannot combine 64 minus 80 because 80 is attached with multiplication, and multiplication has priority over subtraction. So this stays attached, everybody. So let's start moving some things. Guys, everybody subtract 25. And then also, please, subtract 64. If you subtract those two things, I end up getting 55. Again, that negative 80 is attached to the cosine of B, so I keep it as such. Alrighty. Now, everyone, we divide by the negative 80. That's the key. Because it was attached with multiplication, we divide, and I end up getting, when I get that, I have my cosine ratio. Now, again, the beautiful thing is, I'm going to inverse cosine momentarily. And by the way, again, just think of your quadrants here. Where is cosine negative? Well, it's negative in quadrants 2 and 3. So there are two angles that have this cosine ratio. But the quadrant 3 angle is above 180. And so it has nothing to do with this piece right here. It's the quadrant 2 angle that we're going to get. And as a matter of fact, now I know it's obtuse. So everyone, if you would, I'll bring it up. Even though I have it on my paper, I'm going to bring it on up here. And let's inverse cosine. Inverse cosine. Don't forget the negative here, 0.6875. Hit enter, and there it is, everybody, 133.47. And I'm sorry for being redundant on this, of course, but if I decided to use law of cosines and get one of these other angles instead, I would have tried law of sines, and I would have never known that that's this angle right there. It simply would have worked out incorrectly. So, just going to have to remember this piece. If we're trying to find angles and I'm using law of sines, you find the smallest. If I'm trying to find an angle and I'm using law of cosines, you find the largest because of the way the inverses are defined. That's tough, interpreting that piece. Okay. Well, guys, we're now on our way because I have an angle and I have a side across from it. So law of sines. So law of sines to find the second angle. Doesn't matter what you do from here, because when I do law of sines, of course, by the way, let me box that up for you, we know the rest are going to be acute. I don't have to worry about obtuse at all. So let's go for it, everyone. I have 12 over the sine of 133.47. And your choice here, A or C. well, I guess for my purposes, I'll just go alphabetical. So I have 8 over sine of A, I guess. So this to this is the same as 8 to that right there. Okay, very good. Now I'm going to get to that stage before that we've seen. So this times this and divide by that. So I'm going to bring up my calculator and do that piece. And so I have inverse, sorry, not just yet, I got ahead of myself. So I have 8 sine 133.47, and then divide by, what's that, 12. So this is the sine ratio for A, 4838. We've seen this before, where there are two angles that have this sine ratio, one in quadrant 1, one in quadrant 2, one acute, one obtuse, doesn't matter. We know it's acute, and that's the nice thing, we know definitively. And so let's go ahead and inverse sine on that number, everybody. And there it is. So this has to be 28.9 degrees. I'll go 9.4, I guess. So 28.94 degrees. Okay, good. Just about there, everybody. So let me put some stuff in, just kind of thinking out loud with this, see where I am on the board with you. I have 5 pieces of the puzzle. There's only one more left. And just find the third angle. You could theoretically do law of sines, but obviously, guys, they just add to 180. So I don't have this piece on my paper, so I'm just going to go ahead and do that up here. Let's see. So 180 minus, and what did we say, 133.47. Added on top of that, the 28.94. Make sure I have it all typed in correctly, and there it is. I think there's your winner. And so angle C is 17.6. So let's just see, I did this for you. Just want to make sure I've covered all my bases for you, and you're taking good notes. And so when you go back to look at it, you'll be like, all right, I remember that. Mr. Meyer did this, then he did that, then he did that, etc., etc. Well, anyway, no, I forgot the number. Let's see, what was that? 1759. Okay. So 1759, box, and it looks great. So let's see if I need to box anything else up. Yep, one more just to make sure. And there are our 3 parts. Okay, guys. So now you have 5 situations that we've been dealing with non-right triangle trig. We'll kind of review and put some ideas together on the next notes worksheet. Excuse me. You don't have to write this down, but these were the 5. No particular order here. There's the weird one. And then today, 2 more. All right, excellent. Hey, of course, let me know if you have some questions. And certainly thanks for going through this. There's some great math here.